Today we talk about the non-uniform sparsest cut problem, which is a generalization of the uniform sparsest cut problem that we talked about in the second lecture. The non-uniform sparsest cut problem is quite general. It contains both expansion and conductance as special cases. It's also a more general version of the ST min cut problem in undirected graphs. And the algorithm that we will see today is based on linear programming, and it's due to Leydon and Rao. The algorithm is based on a linear programming relaxation of the problem, and the outcome of the linear program will be a distance function between edges. So then we will have to show how to convert this distance function that comes out of the linear program into an actual cut. And to do so, we will use a theorem of Bourgain that shows that if we have any distance function that satisfies the triangle inequality, such as the optimal solution of the relaxation of Leydon and Rao, then it's possible to map all the elements on which this distance is defined into real vectors, such that geometric distances between those vectors reflect the distances assigned by the distance function that we started from, up to a order of log n error, where n is the number of elements. We will also show that once we have this geometric realization of distances, then it's possible to construct a cut relatively easily. It's an argument that is similar to part of the proof of the Chigger inequality. So these three things together will give us an algorithm. The three things being expressing the non-uniform sparsest cut problem as a linear program, which will give a distance function. Then mapping this distance function into a geometrically realizable distance function. And then mapping a geometrically realizable distance function into an actual cut. A similar approach based on relaxation and then converting different types of distances and finally converting those distances into cuts is an approach that works for other relaxations of expansion, conductance, and non-uniform sparsest cut, and also for relaxations of other graph problems. So what we will see today is just one application of a methodology that is very general. In the non-uniform sparsest cut problem, we're given two graphs over the same set of vertices. And in the common definition of the problem, we're looking for some subset of vertices that minimizes the following cost function. The number of edges that are cut by the partition S v minus S in the graph G divided by the number of edges that are cut by the partition S v minus S in the graph H. But in our course, to maintain consistency with the notions of expansion and conductance and sparsity that we defined in the first couple of lectures, we will use a different normalization, and we will multiply by the ratio of the number of edges of H and the number of edges of G. The problem is also well defined for weighted graphs, in which case this will be the total weight of the edges of H, this will be the total weight of the edges of G. This will be the weight of the edges with one endpoint in S and one endpoint in V minus S for G, and this will be the weight in H of those edges. Let's see some examples of instances of this problem. So in this problem we have these two graphs G and H defined over the same set of vertices. Let's say H has only one edge, say between some vertex S and some vertex T. Then the only admissible cuts of the vertex set into S and V minus S are cuts where the vertex S and the vertex T are separated, because otherwise in the denominator of the cost function we are going to see 0. So the cost function will have a division by 0. So this means that we only allow partitions S, V minus S in which the vertices S and T are separated. And for those partitions, we're looking up to normalization at the number of edges in G that go from S to V minus S. So this is just the ST min cut problem in G. So one way to think about the non-uniform sparsest cut problem is as a more general version of the ST min cut problem, where we're given many pairs of vertices that we would like to separate, and those pairs of vertices are the edges of H. And then we're looking at the ratio between the number of edges that cross the cut and the number of pairs that we have actually separated. If G is regular and H is a clique, then after looking at the normalization, what we're getting is just the quantity that we previously called the sparsity of S. Because if H is a clique, the number of edges with one point in S and one point in V minus S will be the product of the size of S and the size of V minus S. Now we show that the sparsest cut problem can be used to approximate the conductance of a graph. So say that G is a graph of which we want to estimate the conductance. Then we construct a graph H, which will be a complete weighted graph, in which the weight of an edge UV will be equal to the products of the degree of U and the degree of V in G. Then let's see for a subset of vertices what is the non-uniform sparsity of this set. In the numerator, we're going to see the number of edges in G that go from S to V minus S. In the denominator, we're going to see the summation over all U in S and V not in S of the weight of the edge UV, which is du times dv. And so then this breaks up as the summation for U in S of du times the summation for V not in S of dv. And this is the volume in G of S, and this is the volume in G of the complement of S. The normalization is going to be the total weight of the edges in H divided by the total weight of the edges in G. And this will simplify to being just the volume of V in G. Now for a given cut S V minus S, let's call S the side of the cut with a smaller volume. Then this normalizing factor volume of V divided by volume of V minus S is between 1 and 2. And the ratio edges in G from S to V minus S divided by the volume of S is the conductance of S. This means that the sparsity of S is up to a factor of 2, the same as the conductance of S. Now the optimum of the sparsest cut problem on input G and H is the minimum of the sparsity over all sets. And optimizing over all sets, or optimizing over all sets whose volume is more than the complement, is the same. So then when we optimize over sets S whose volume is smaller than the complement, sparsity of this instance is up to a factor of 2 the sparsity of the graph G. Let's see now how to reformulate this non-uniform sparsest cut problem so that we can derive a linear programming relaxation of the problem. Optimizing over cuts is the same as optimizing over Boolean vectors, because we can associate to every set a Boolean vector which is just the indicator vector of the set. In that case, the total weight of edges going from the set to the complement will be the summation over all pairs of the weight of the edge UV if present, times this expression, which will be 1 if UV crosses the cut and 0 otherwise, and the same for H. We now make the following observation. If X is a Boolean vector, this difference xu minus xv can be thought of as a distance function between vertices uv, and it's a distance function that satisfies the triangle inequality. This triangle inequality will just follow from the triangle inequality between real numbers. The idea of the Leydon-Rao relaxation is just that instead of optimizing here over distance functions that can be obtained from Boolean vectors through this expression, we're just going to optimize over arbitrary distance functions that satisfy the triangle inequality. So again, this is the non-uniform sparsest cut problem as defined, and the Leydon-Rao relaxation will be the problem where we replace xu minus xv with a distance between u and v, and then we optimize over all possible distance functions as long as they are asymmetric, which means that as long as they satisfy the triangle inequality. This seems like a very loose relaxation, one where you allow distance functions that look nothing at all like Boolean distance functions. So it's unclear that this is at all useful in approximating the problem, but it turns out that this can give a fairly good approximation. Let's give a comparison between the way we obtained this relaxation of Leydon and Rao and the way we see lambda 2 as a relaxation of the sparsity problem. So let's look at a special case in which the graph H is a clique. Then the sparsity of the input G H is just what we defined previously as being the sparsity of G. When we proved the easy direction of the Chigger inequality, we observed that lambda 2 can be also characterized in the following way, as being the same as the minimization problem that gives us the sparsity of a graph, except that instead of optimizing over Boolean vectors, we optimize over real vectors. And instead of just taking the difference, we take the difference squared. For Boolean vectors, taking the difference or taking the difference squared is the same. The Leydon-Rao relaxation, in the case in which H is a clique, will be the same expression, but where xu minus xv is replaced by the distance between u and v, where d is arbitrary. And those two relaxations are completely incomparable, because what we get as an arbitrary distance function might be not realizable as differences of entries of a real vector. And when we look at differences of entries of a real vector squared, those need not satisfy the triangle inequality. And interestingly, we will see that graphs that are bad examples for lambda 2 are graphs where this relaxation works well, and vice versa. The way we formulated the Leydon-Rao relaxation, it was clear that it's a relaxation of the non-uniform sparsest cut problem, but it's not at all clear that it's a relaxation expressible as a linear program. But here it's how to express it as a linear program. We observe that for every distance function, if we multiply every distance by the same constant, we don't change this cost function, and we still maintain the fact that we have a distance function that satisfies the triangle inequality. So without loss of generality, we may assume that the optimal solution to this problem is a distance function for which the denominator here is precisely equal to EH divided by EG. Now if we put that as a constraint, the cost function will just be this numerator. And then we're going to have the constraints that the distances have to be satisfying the triangle inequality. And now we have a linear program. We have a linear cost function, linear in the variables which represent the distances. And then we have linear constraints on the distances. And conversely, every distance function that satisfies those constraints will be a symmetric, and its cost in this expression will be precisely this cost. So this formulation and this formulation are precisely the same problem.